So for the penultimate lecture in the deconstruction series, we are organizing with Boris Amzeyan. We are truly honored to welcome today Werner Sobek, a major figure in contemporary architecture and engineering, whose commitment to radically transforming the way we design and build has become a point of reference. It is also with particular emotion and honor that I welcome Werner Sobek today, as I had the privilege of working alongside him both at the ILEC Research Laboratory and within the Werner Sobek Engineering and Architectural firm. Werner Sobek is an architect, engineer, and emeritus professor at the University of Stuttgart, where he directed the ILEC Institute for Lightweight Structures and Conceptual Design for many years, after having merged the EL funded by Frei Otto and the ICA by Schlaich. Werner Sobek has, for over 3 decades, been developing a pioneering vision of architecture rooted in technological innovation, structural lightness, and sustainability. His approach is defined by an uncompromising commitment to reducing resources use, achieving zero emissions and zero waste, and embracing innovation. In both his built work and his writings, he emphasizes the urgent need to rethink design practices. He advocates for a systemic transformation of the building sector, supported by practical strategies such as industrialized construction processes, prefabrication, and the development of innovative systems such as, for example, passive and active houses. Beyond technical performance, his thinking opens up new perspectives on the role of architecture in addressing today's environmental challenges. What forms should an architecture resolutely oriented toward the future take? What technologies can help us reconcile the desire to inhabit with material restraints? How can we anticipate the needs of future generations through the decisions we make today? These are just some of the questions Werner Sobek should address in this lecture, The Future of Architecture and Building Technology, where he will outline the profound shifts required to move toward a sustainable, desirable, and replicable way of building. Please join me in giving a warm welcome to Werner Sobek. Thank you.
Thank you. So good evening. Mon français c'est absolument limité, so je m'excuse pour continuer en anglais. Thank you very much for inviting me to come here to Saint-Étienne. I have some roots in Saint-Étienne because 15 years ago we designed a building together with Finn Geipel here, which is a building which shows 14,000 triangular pieces of metal or glass for the covering of the facade. And since the very beginning of my career, I always had a project in France. The very first was La Couverture des Arènes de Nîmes, where I was the ingénieur responsable pour tout. And then we had an École Nationale Décorative à Limoges, then a building in Saint-Étienne. And the last building I was responsible for was a residential building in close to Saint-Étienne, in Isanchon, up in 900 meters height for a friend of mine. So, but however, since I had to speak in French and to follow French codes and so on, my active French got a little bit lost, so I continue in speaking English. I'm very sorry for this. Mark asked me to squeeze a little bit of content in front of the lecture I was planning to give, and this content is explaining what ILEC is standing for. So ILEC is the institute I founded, the Institute for Lightweight Structures and Conceptual Design at the University of Stuttgart. And this became famous in the world. And why did it become famous and what is behind it? So let's talk, before I come to the main topic of my lecture, a little bit about this ILEC. I use very often the abbreviation ILEC because this is what is known all over the world. It even happened that someone from Africa wrote a letter to ILEC Stuttgart, and the letter arrived. not by email, but by post. So it was a luck that in 1916 in Germany, in the University of Stuttgart, they founded the first chair, means an institute and a professorship, for the research in concrete, to give concrete a scientific basis. What is it? How does it function? How can we calculate this? And since 1916, the University of Stuttgart had the popes of concrete, besides the French colleagues, of course, Freycinet and others, many others. But for Germany and the rest of the world, these professors in Germany researching concrete were the most prominent ones. And the books, the handbooks they published have been translated in more than 20 languages and so on. And Emil Mörsch was the first one in 1916, and I was number 5 in the engineering department. Parallel to this history, in 1963, the University of Stuttgart founded out of nothing a new institute in order to bring Frei Otto, a famous young architect, but already famous, not for his architecture, but famous for the way he was thinking about architecture, to Stuttgart University, and they founded an institute for lightweight structures in architecture. And Frei Otto was the first one who combined structures we find in nature and technical structures. So he was researching spider webs, and he designed then nets made out of steel cables, spanning and covering soccer stadium, etc., etc. He laid the basis for the understanding of these in the year 1963, where we had no computers, unbelievable complicated double curved surfaces and shapes by doing soap film models, like the famous mathematician Plateau in Belgium did. To understand what we are talking about, they made soap film models. And Frei Otto studied these soap film models on the way, on the path, to learn about minimum structures, means to learn about structures showing minimum weight. Why? This was unanswered. This was more a theoretical, let's say, objective. Where is the minimum and what technologies yield to that minimum? And I had the luck to be the successor of Frei Otto in 1995. And then when the professor for concrete engineering, so the first thread I was talking about, retired, the university offered me also this chair, so I had 2 chairs but only 1 salary and 2 institutes. But it was a very famous and very, let's say, powerful situation for me to have 2 chairs, 2 institutes and 2 teams of assistants. And then I did, against many, many, let's say, obstacles, what I always wanted to do, I merged these 2. And I said, this separation of the École des Beaux-Arts and the École de Polytechnique yields an absolute nonsense, because 2 people educated in different objectives, in different value systems, in different languages, where the students never talk to each other. After getting their diploma, they meet on a table and then they should talk to each other. This can never work, because the one lacks the understanding of the other and the other way around. And we overcame this at ILEC. At ILEC we said, we offer lectures and possibility to studies for everyone, because it is called université and not monoversité. And this was very successful, revitalizing université. So we had students coming from aircraft design, from machine design, from sociology, from architecture, from structural engineering. They all worked together. Our doctoral students doing their doctoral thesis came from different institutes. This was a blossoming success. So this was the roots of ILEC. It was lightweight, interdisciplinary teams. And what we came up with is the lightest structures you can imagine. This is only a few slides. This is concrete. and the diameter of the holes is maybe 3 to 6 centimeters, and the thickness is 1.5 centimeters. And this is spanning over 6 meters. Super light. You cannot undergo that lightness. And of course, we teach how to, this is not elect, this is in the 50s. Pierre-Luigi Nervi and Myron Goldsmith designed this competition entry. Unfortunately, they did not win, for a bridge over the river Tiber in Rome. But what you see is that at these times, lightweight meant that we shape the building elements in the line of moments. This was what people could understand, not having computers. It already yielded to relatively light structures, but not to what we were capable to do later on. So for example, in the year 2003, using computer methods and finest production methods, we designed this. This is like a soap bubble, but the diameter is 8 meters. And it is laminated glass. It's a 2 millimeter shield of glass, and then there's 6 millimeter glass spanning over 8 meters. So the thickness to span ratio is 6 plus 2 is 8, 8 to 8,000, or 1 to 1,000. This is like building with a sheet of paper, 1 to 1,000. This is even thinner, like as you find it in the fuselage of, for example, an aircraft. And still, it is not the optimum, because you see that this, as a research object, double curved panes of glass, no metal in between. We developed the glue, etc. But it has single supports, and wherever it is single supported, all the forces and the stresses concentrate here. Means we have stress concentrations here and here, but not in between. Now, what we could do is we could punch holes in the glass and say this material is not needed, because where there is no stress, we don't need material, which is difficult with glass. So we did it, as you already saw, with concrete. On the left side, this is a sheet of whatever it might be with single supports, and you see the stress concentration. It is obvious that here you have to have more material than here. So here you have more material than here, and here you have more material than in the rest of the structure. So this is part of this 6 meters spanning 1.5 centimeter thick concrete thing. This needs very refined engineering and computer methodologies and also production techniques, but it shows you where the end is. This is what we can do nowadays. And ELEC laid the basis for it. Now you might say, okay, all these cafeteria shelters, we know that. Is it also applicable for reality? Take the idea that there is no material where there is no stress. And then we have a regular slab, for example. So this is, in reality, spanning from here to there about 6 meters. And it's obvious if you have a support there and a support on the other side, that then the highest compression is at center and the highest tension is here. But then the flow of forces changes and the stress level changes. So we invented holes in a concrete element, but of course no holes produced with inlays of plastic, because recyclability was always a headline. We always design things so that they are 100% recyclable. So we had to invent sculptures, forms made of mortar or cement, which we then lay in the formwork, then we pour the concrete, and the result is then this. This is 40% of the weight of a regular concrete slab. It is 10% thinner and has the same load-bearing capacity. So it is simple and easy to save half of the material compared to what we find somewhere else. So it is in detail, many tests in reality, but if you do so, if you have these, in that case it is spherical bodies, you can do them like potato bodies, whatever you want. We made it simple in the very first steps and made it spherical. But if you have spherical situation like here, the question arises, what is the densest type of package of spheres? And then you end in very deep mathematical problems. It's the theory of packaging spheres. this is an example. So we need the influence of mathematicians to our research, and our doctoral students, they do models then, numerical ones, digital ones, and real ones, in order to understand how can we pack different diameters of these concrete hollow spheres so that later on they form a hollow piece inside, for example, a girder or a plate or whatever. And if you cut out of such an concrete element a part like this and give it to a structural engineer and say, okay, this is what we invented, could you do a calculation following the code? Then it might be very difficult, definitely. But we also developed the technologies to do so. So we had the idea, we developed the technology to produce it, we developed the technology to calculate it, and now it is applicable. And we applied for different buildings now in the meantime. This is just a shot in order to show you that these bodies do not have to be spherical. They can take any shape, which is a sense-making shape. And sometimes, and then I come to an end in introducing you to the way we thought at ILEC. Imagine if you have, for example, an arch under its dead weight. It's very simple to define the shape the arch should have, so that is an optimum shape, an optimum geometry. But if you make the arch thinner and thinner, and if you have an asymmetrical loading, the arch is going to collapse. So this non-symmetrical loading is typically, which is causing buckling and large deformations, the design problem for the engineer, not a design problem for the architect, for the engineer. And what do? They add mass. They say, okay, if under dead weight the arch is thin, but unilateral loading, it buckles away, then we have to add weight and material so that it stays stable. And this is why many arches are so thick. Now I said, this is the traditional solution. Never believe the traditional solution. There must be something else. And I said, if we would have a technique which bends the arch in this direction, exactly in the point of time when a unilateral loading drives him to this, then the natural deformation, which is this, and the artificial superimposed by Werner Sobek is this, and the sum of both is 0. Nobody believed that. So I had to convince many, many people. Then I had to collect about 50,000 euros. And then we designed not only an arch, following the functioning arch, we designed the thinnest wood shell ever built. So imagine, this is from here to here, it looks scientific. From here to here, 10 meters, each of the supports. So the diagonal is 14 meters. This is from here to the wall at the end. And the thickness is 4 centimeters wood. Regular quality. And indeed, it stands still under its dead weight. And as soon as we have a unilateral snow load or wind, it would break. It would fail. So what we did is, we had about 10 or 15 tiny sensors below, and these measure strain gauges. They measure the deformation, why the thing is starting to move. From the deformation, we calculate the stress field, which is going to happen. Then we create artificially an anti-stress field, which is causing this, and the sum is 0. And the anti-stress field we are causing in order to drive it to this direction is by moving these points, the support points, by a few millimeters in the X, Y, Z direction. Under standard condition, this wooden shell would have a thickness of 24 to 30 centimeters. Introducing our technique, we drive it down to 4. Means we save 80–85% of the material, and we replace the material we saved by energy, which we need from time to time when the snow is falling in a non-symmetrical way to move these support points. But the energy we need is very small. It is very small. So what we did is we replaced building with material by building with energy. This does not mean that you now should design every of your buildings you are designing with an energy mechanism. I'm telling you that story to make you open in your thinking, that it is not about just adding material when it becomes critical. No, sometimes it is much better to take material away and replace or solve the problem with something different. And this very often makes a lot of sense. So see, if we have, for example, a unilateral snow loading and we draw the stress field of this, means the loading, the internal loading of this shell onto a plain sheet of paper, then we would see something like this. This is the projection. This is the critical corner. Since it is symmetric, we have the other one. The shell will break definitely here. Here at center, it's relatively smooth. Now the problem is by moving these support points a little bit to dampen this stress field and to make it very, very homogeneous, and this is what we do here. So putting a little bit of energy to move a little bit of support point, and the problem is gone. This is not only academic. As Mark told you, I'm an architect and an engineer, and many projects I'm doing, I need to combine those two things in order to come to a solution. So one of the famous buildings I designed in the last years is this. Now you have to imagine this is 250 meters high. And what is it made for? The building also goes 50 meters down into the soil. So it's a vertical stick of 300 meter length, and it is used to develop and to test high-speed elevators. Elevators which do not have a counterweight. Because if you have an elevator and a counterweight, you have a lot of material to transport it. It's very heavy, blah, blah, blah. So we said, if the counterweight is the problem, no counterweight. But how can you do a cabin of an elevator without a counterweight and without these long cables? You need to remember the magnet train technology, where the train is running on a track without touching the track. So we transferred, not us, but ThyssenKrupp, the technology of the magnet train to the vertical situation. And now the cabin is running up and down without touching the shaft of the elevator box, just by magnetic, electromagnetic issues. So now the following thing is, when they want to get a certification, for example, in France to sell their elevator there, then they typically have to get a certificate by a couple of specialists. They come to the place and then they want to see the elevator running, they do their measurements, and finally, after doing all these tests, you get a certification to use it in France. But most of these tests are in a still standing tower. Now, if this tower is moving due to wind action, you cannot do the tests. You have to pay all the specialists, but they cannot run the tests because the tower is moving. So what we did is we remembered the shell, we remembered this action, and we said, okay, in order to keep it away from moving, we can make the tower super fat and super heavy, or we manipulate it. So what we did is, here in a height of 200 meters, inside there's a steel block, 200 tons of steel, which is hanging on a cable, and there's two high-speed electro engines which are capable to move that slightly, only slightly. And we move it in that way, like a pendulum, that this makes the tower standing still. So we save endless material because we can design the tower very soft with a little material only, And the huge deformations that would occur under wind loading, we dampen them down to zero with this action. Adaptivity is how we call that. Now the thing happened when everything was done, the ThyssenKrupp engineer said, this is a great idea, we really loved it, machine engineers, so permanently smelling like machine oil, etc. White-faced because they are always working in their laboratories in the darkness of the elevator shafts. And then they said it would be great to set the tower into swinging so we can test the elevator even under earthquake conditions. And then we found out that this is doable, of course. We just have to move that weight in a way that the tower starts swinging. Then the engineers of my company, they went to the administration of Rottweil, this is where the city said, we need an additional building allowance. We are now starting to make the tower swinging. And this is the first tower in the world which might destroy itself if the software does not work. So this made then the people in the administration white-faced. They said, we don't want to have this. So we had to convince them that it really works, etc. And now you can do whatever you want with the tower. If there is wind, you can make it standing still. And if there is no wind and you want to simulate earthquake, then you make it moving. By 200 millimeters left to right. This is a lot. When you stand on the top and it moves 200 millimeters, then you probably run away and start crying. It's concrete. But this is how we think, yeah? So a short introduction on how we think. It is a generalized thinking. It is interdisciplinary thinking that is trying to understand how the people from the other disciplines think, what their value systems are, what their objectives are, what they learn, what they don't learn, etc., and bring that all together and then always ask the critical question. I do not believe what I heard, as long as I did not fully understand it. And if their solution is a standard solution, there might be another solution, which is even better. So this is our philosophy on how to approach. So we designed many, end of ILEC story. It took a little bit long, huh? Mark, is that okay? But now you know what ILEC is doing. And my successor, since I'm retired, since a couple of years, is continuing that work. Now, Mark asked me to talk a little bit about the future of architecture and building technology. And this is a very critical thing, because I could make you sleepless, I can make you hopeful, I can make you happy and lucky depending on where I emphasize what I talk. It is the future strongly depends on a couple of issues like the growth of the population, the global warming issue, the resources issue, etc., etc. And of course, they are typically interconnected. So, standard city of our times. Whether we could be proud on this or not, I think this is a self-answering question. The picture stands for the growth of population, which rapidly grew from the year 2023 of 8 billions. At the beginning of the last century, it was 2.3, and will end at around, depending on whom you ask, 10 billions at 2050. So the population research defines one generation as 25 years. Means within one generation, the world's population will grow by 25%. This means something. These people will get born in Africa and South Asia, most of them, South America, but I will tell you that this means also something very dramatic for you. And this is part of the lecture, part of what I'm talking about. We have to get a consciousness what the sheer numbers mean. And not get anxious, as I told you. Not get anxious, because this would be the standard answer. I will shock you, you get anxious, you get some alcohol and then fall asleep. No. Take the numbers, understand the systematic behind it, and then take action. So the main question is, in order to imagine what does this mean, what is the net growth of the population per second? This is the ELEC style. 10 billions in 250, okay, why not 12, as many say? Because there will be so much hunger that many hundreds of million people will die by hunger, guaranteed. So our prognosis is something like 10 billion, plus minus. But what does this mean per second? It's very important for you, because there's an increase. An increase means these people will ask for a built environment. They will ask, dear architects, your profession is build home for us, the new arrival on the planet. But what does it mean if you have to build a home for how many per second? The shock is 2.4. 2.4. 4.2 about are born, 1.6, 1.8 are dying, unfortunately. So the delta is 2.4 per second. Now, what does this mean, 2.4 per second? It means one apartment per second where two people live. And how much material does this need? If they do not live like this, as the cage people in Hong Kong, which pay 200 Hong Kong dollars per month to live in the cage. And this is a privilege. They can afford to rent a cage because there they can close the door at night and get not rubbed out or killed at night time. This is a secure place. Nobody of us wants to live in. But these inhabitants have a living space of 1.5 square meter, which costs about $500, this metallic cage. No toilet, no shower, nothing. It is the minimum to survive, but they already call that luxury. If we say, no, this is not what we want to have something like the standard we have in France. Yeah, but what is the building standard in France? What does it mean? And this yields to the essential question, how much building material does every one of us own? It's essential for an architect. See, you never learned that. Yeah, but this is the question number one. How much material do we need to build home for these people? Now, a typical citoyen in France has about 440 tons per capita. Same in Germany, in Switzerland and in Austria, where they have all these tunnels and whatever, dams and so on. Difficult situation, this goes up to 500. An average industrial country in the Western world has 335 tons per capita. You can note 335 and then add plus minus 10, plus minus 15, because nobody really knows the dead weight of Notre Dame in Paris. And nobody knows the dead weight of your nice Gare SNCF. Yeah? So you have to estimate that by several scientific-based means, but average is 330 tons. So now, if we have these 2.4 people net increase per second, multiplied by 375, it's about 1,000 tons per second. Building material. This is not resources. It's building material, which you gain out of resources. So if you have a tree in the forest with a dead weight of 10 tons, this is the material resource. In your wooden house, you find maximum 30%, which is 3 tons. This is the building material. The rest is lost on the way out of the forest to the house. Don't talk about this now. But that means The amount of 1,000 tons building material per second means 1,200, 1,400 tons of resources, which have to be scratched out of their surface. The critical zone, as the famous French philosopher Bruno Latour said, la zone critique. This is what you have to get out of there. And the question is this really doable? And how much material do we find on the world, actually? Now, in 2023, it was 970 gigatons. Gigatons means 1 milliarde, or the US would say 1 billion, which is absolutely mad, that the people now messing up milliarden and billions and whatever. So the engineers have a nice abbreviation for this. I will come to that later. 970 gigatons is the existing. Now the increasing of the population with a Western standard in the next generation, these 2 billions, means another 670. Now you will ask the question, 8 billions, Milliarden, have 970, and the 2 Milliarden increase has 600. How can that be? This is because in these 970, there is something included what we call the third world, or another stupid expression, the global south. Out of the 8 billion people, 8 Milliarden, there's 1.4 on the high standard of 330, 350, and 6.6 have 75 tons per person only. These are the countries where we say, okay, we have to reduce the increase in population growth by education and health. But if you bring education to these countries, that means you have to build the schools, you have to build the universities, you have to build the houses of the teacher, you have to build the roads going on to the water supply, you have to build the pipes for the wastewater supply and the sewage plants. Means you have to build the difference between 75 tons in the global south per capita and 330 in the industrialized countries. So if you take that difference and multiply it with 6.6 Milliarden, then you come to the number, which I call catch up. This is 1,700 Milliarden tons. So, and if you add that up, that would mean if in the year 2050 everyone would like to have the building standard of a Western country, then you would have to build the existing world 2.3 times in addition. You don't need to study mathematics to do these calculations. You have to ask the right questions. Nobody told you this. I asked the question, why? No scientific magazine is talking about. And this is so simple. Just multiply the need of material or the need of food with the number of people and compare it to what exists. And then show the difference to what is needed. And then you become much more wiser then. So this is how we work at ILEC. We talk to population researchers. We say, are these numbers right? Are these wrong? What is your estimate? We talk to material scientists, to economic people about what is the industry producing on building materials in China and Japan, somewhere else. And then we add all these numbers up and we come to these conclusions. So now it's clear, this is absolutely impossible. The material is not there to build the existing world another 2.3 times in one generation. So what is the conclusio? We need to build for more, definitely, with less. As Mies said, less is more. We say, I say, build for more with less. This is not bad as a headliner. This makes you now thinking, We need to build for more with less. How can we do that? And something I will point out in detail later on, consider the built environment as a part of nature. We, when it comes to the Enlightenment in the 1600s, 1700s, when sciences arose and scientific, let's say, disciplines started to be defined like medicine and mathematics and physics and whatever, and many things have not been defined and are not really researched now because this discipline pattern is very rigid. These early scientists, they said, okay, what is nature? What does mean nature? And they defined nature as an object to be researched, to be used, to be explored, to be destroyed. And from then on, nature was not an essential part of the human's living. Nature was the environment. It was an object, and the human being became the subject. And the subject was using the object, yielding to the situation we are in now. The subject misusing the object. At the end, destroying the object from which he is living from. And this is what we have to think about and what you have to discuss amongst yourself and with your teachers. Is our approach to think about nature as an environment the right one? Why do I think about a forest in another way as I think about my arm? Because this is mine, I need it to survive. Yeah, you need the forest too to survive. So rethink this relation. It's a big question among scientists, but they make it more scientifically complicated actually than to bring it to a solution. The solution must come from a societal talk, from a discussion in between amongst the people, definitely. And I condense this. Very often I do such a thesis, I nail it on the wall. Thesis number 17 is, in Latin, natura mensura est, which is exactly what I said. In the Enlightenment and before Enlightenment, people said, Deus mensura est. God is the measurement. We cannot do nothing which is against the idea of God. Then in the Enlightenment, when the human being became homo mensura est, I'm the subject, I'm governing the world, I'm exploring nature, etc. So this changed from Deus mensura to homo mensura. And what I say is we have to come to a situation where we say natura mensura, it is about nature, because nature will always survive, with or without us, but we will not survive without nature. So, we were talking about material consumption. I gave you a short insight and which question to ask, and we learned that we have to build for more with less. How can we do that? The story of Ile gave you some first ideas. And together with material consumption, we have the problem of waste production. In many, many cases, when you produce out of a material, a building part, you create lots of waste. Imagine the jacket here. The jacket comes from, the fabric comes from a roll, 500 meter long, 2 meter 20 wide. And then to cutting pattern techniques, you cut something out. And the cutouts, these are forming the jackets. And the leftover, this is the production waste. In many, many processes, also in the building industry, think about the wood industry, you have production waste in the level of 50%. This is another topic you have to attack and to work on. It's not only about the minimization of the weight in the building, it's also the minimization of the waste we are producing in the production process of the building material. Then there's the story about energy, which is the biggest misleading of the people I ever thought. Intentional misleading, and of course emissions. So see, you learned already a lot about this, as Mark Hyman's told me that, about avoiding this waste. How can you avoid this waste? There's two simple techniques. Not to tear the building down, to reuse it, or to build in a way that this type of waste does not exist or occur. Means in a recyclable technique. I call that compose and decompose. Bring the different materials together in a way that it is easy to decompose them and then to recycle the different single quality materials. But if everything is bonded and glued together like here, recyclability is more or less zero. So not tearing the building down, reusing it, is something we did relatively often. And especially when it comes to a weapon factory where they produced munition. Me being an anti-militarist, it was quite clear that I have a lot of fun in doing this, and we turned this weapon factory in an institution of arts, in a school, the Center of Arts and Media in Karlsruhe. So not tearing it down, reuse it. And the idea of recycle means build in a recyclable way, which we do not typically. Car industry is obliged by law in Germany that their cars have to be recyclable by 80%, 85%. So they started doing this in the 80s of the last century. Building industry has no idea about how to do that. Therefore, we started already 30 years to create buildings, to plan buildings, to build them in a way that they are recyclable. Exactly with these techniques. Easy to compose and easy to decompose. And the shining example of this is the house I'm living in. Some of you might have seen that. This is my private house. So this is super light because the dead weight is 16% of a building in the same size built with traditional technologies. So I saved 84% material. I do not need energy from outside because we produce the energy by ourselves. It's all solar and then electric. And the house has no chimney. So it is zero emission in the use phase. And it's 95% recyclable. Because all the joints are simple by bolts, you can see them. You take the bolt out and the house falls apart. There is no multi-layer gluing and nothing like this. Many questions arise. So where is the light switch? If you have a light switch in the wall, then there's a cable in the wall going to the light switch. Typically not reusable. Difficult to recycle. So we said we have no light switches. It's very simple. So how do you do that, having no light switches? You have a, how do you call it, a handheld, which has the big advantage that if you are on the floor number 4, you can switch on the light in the floor number 1 without running downwards. Or you can open the windows all with the handheld. Now this is trivial today, but this house is 25 years old. It was not trivial at these times. And as I said, it is minimize weight, minimize waste, make it recyclable, and we come to the topic later on, zero emission. Comparable here, minimized waste, minimized weight. This is a house, a unit I designed. This is the biggest research project in the history of Switzerland, which is 100 million Swiss francs. And the University of Dübendorf and Zurich, they built these platforms. And inside there is a core with piping and scientific apparatus, etc., etc. And then they invited 12 architects. I'm the only non-Swiss, 11 Swiss people, and I'm non-Swiss, to add some things. which have a scientific background. So some of them have hot water cascades in order to use warm water, still use it to use wastewater, warmth, etc. And I said, let's design a building which is made 70-75% out of recycled material and which is fully recyclable. And this is what ended here. So the facade here, this is copper sheets from different buildings which have been destroyed and demolished. We collected that, we cut that to size. I had to combine the colors in a way that it looks nice, and the interior is the same. It's all recycled, what you see. Everything is recycled. This was concrete before, this was bricks before. Out of bricks we made new concrete. This is wood which we recycled, aluminum which we recycled and made these plates out of it. The only thing which is not recycled is the glass. And there are wonderful things, for example, like this. This is recycled material. To give you an idea, this is about 3 centimeters big, so it's a close-up. What is this? This is PET water bottles, used water bottles, and we collected them, transparent with blue caps. We shredded them, we melted them up to 70 degrees, poured that honey-type liquid into a big steel basin, let it cool down, then slice it into pieces, 2.50 meters high, 1 meter wide, 10 millimeters thick. And this is the cladding of the toilets and of the showers. It's recycled material, and it looks super beautiful. It's just plastic. And of course, we did not glue it to somewhere. We bolted it in order to make it watertight, blah, 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 so that it can be reused or recycled easily. And if you have water bottles with red caps or yellow caps, then the marble looks different, but it's plastic marble. Energy. The story with the energy, I'm already exceeding the time frame. But as long as nobody falls asleep, I continue. Is that okay? We all have an energy problem. Eh? Do you know why? You learn to design energy-efficient buildings. Did you ever ask why? No. Isn't this crazy? You pack all the buildings you design in styrofoam and whatever natural and mineral wool and so on, and you never ask the question why. Why are we urged to be energy efficient? Now, when did this come up? I'm talking not about France. France took a separate way. I'm talking about the rest of Europe, especially Austria, Switzerland, Germany, the Netherlands, and these countries. This happened when King Faisal of Saudi Arabia confiscated the largest oil company in the world, Aramco, Arabian American Oil Company, which was owned by 4 American oil companies. And in the year 1970, Faisal, powerful enough, he confiscated that. The US said, now we bring war to Saudi Arabia. Then they found out we can't do that because we depend on that oil too. So they made a deal. He had to pay the 4 former owners off over the next 10 years, what he did. So he paid for what he took. And then he promised to the United States that he is selling petroleum only in dollars and not in Saudi riyal. What does this mean? The US got the so-called seigniorage effect. Means like someone who is printing money or who is giving coins to his people, takes the advantage that the coin is nothing worth, but the person who is getting the coin has to pay a lot for it. If I have the seigniorage, and you want to have 10 euro from me, I give you a sheet of paper with 10 euros, which cost me 1 cent, and you have to give me the equivalent of 10 euro, which is something. So this is the seigniorage. Means if you, as the US, have the seigniorage on the oil, then you earn money and you don't have to do anything for it. You just print dollars. And the advantage which brought them this deal is 3,000 Milliarden, 3,000, and then T exponent $9 for more or less free in the last 60 years. But now the power on the oil was in Faisal's hand. When the Israeli had the Yom Kippur War and Europe was supporting Ukraine, then they stopped delivering oil to Europe, which we call the oil crisis. And then the politicians in Central Europe said, oh, we are very depending from Arabian oil. We have to overcome that. We have to get oil from Venezuela, maybe from other countries, but the majority was still Saudi Arabia. And then they said, and then we have to reduce our consumption. So then they took the glasses and looked who should reduce the consumption. The car industry, no, because the car industry is powerful. The energy industry, no, because they are politically powerful. The building industry, they have a very weak lobby all over Europe since decades. So they said, you are the ones which have to save energy. These first energy laws, or the energy reduction laws, do not contain the word nature. Global warming, of course not, 1976. This was an economic, strategic thing in order to reduce the import of petroleum from those countries, in order to not experience another, in this case then a third oil crisis. This was the reason. It was nothing to do with nature. And the automobile sector, the aircraft sector, the energy sector, they should have been urged to save energy too, but they were too powerful. So it was the building industry. And since then on, architects started wrapping styrofoam and mineral wool around their buildings. And then in the year 1995, the Kyoto Protocol was undersigned. What does it mean, Kyoto? For the first time ever, most nations in the world agreed that we have an emission problem. But instead of attacking the emissions and telling the people, now we are introducing a law, you have to reduce emissions, the politicians thought in the wrong way. They said, okay, we sharpen the energy efficiency laws because a lot of energy is burned, is combusted, and is causing emissions. So if we reduce the combustion of gas and oil, then we reduce the emissions and we are doing a good work. Yes, yes, but only on a part of the problem. Only on a part of the problem. Nobody really said, the energy problem is a trade problem, a trade strategic problem. And the emission problem, this is the real thing we have to attack. But nobody did. It took then up to 2015 to the Paris Treaty, where for the first time ever, many, many nations, I think it was more than 150, signed a contract or a declaration that they understand that we have an emission problem and that they are going to reduce the emissions from, at that point in time, maybe 50 gigatons per year to 2050 down to about 5. This is the point. The sun shines, the sun only, 10,000 times more energy on the globe as the human being needs for all their activities. 10,000 times more. Plus geothermal, plus wind, plus whatever, wave energy. We have energy like hell. We do not have an energy problem. Definitely not. We had an energy supply problem with this King Faisal thing, but we have an emission problem, and this is what we have to focus on. However, if we change our, for example, way we produce is the wrong word, we transform petroleum and gas to, for example, electricity. If we want to overcome this and base everything on sun and wind and blah, 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 then we run into a certain shortage of the electricity supply. And this is what we have to, let's say, balance, what we have to live with in the next 20 years. Not in France. You have the nuclear power plants. You have probably enough electricity, so you can even sell it to Germany, but the Germans don't. So energy, still, what we can do is, if we work on our buildings, that we, for example, do the roofs of these with photovoltaics and with heat exchanging elements, so that we designed a settlement which is 340 apartments, which is a plus energy settlement. There's no chimney. This, by the way, all recyclable again, and so on and so on, but plus energy. It's very, very simple. And the advantage is we produce the energy on site. We, of course, have to solve the problem on how to store the energy when we have no sunlight for several days, or reduced sun impact for several days, but this is another topic. But the main thing is the emissions. And then, as I told you, there is no law, no legal activity to reduce the emissions in the building industry, only the energy efficiency thing. But the built environment stands for 52% of the emissions. 38 comes from buildings, and about 15 comes from infrastructure. Now, in infrastructure buildings, you don't need to heat something or cool something. No, these emissions are the so-called gray emissions, which occur when you produce the materials, transport them on site, erect the building, might it be a bridge or a house or whatever. So this is the gray. And then the emissions emitted in the use phase, this comes mainly from the buildings, heating and producing warm water. We can roughly estimate this heating and cooling out of these 52 is, depending on the country we are talking about, 25 to 30. But now the gray emissions of the buildings is a remarkable number. This is 12 to 14. And the same is true for the infrastructure. So producing cement and steel and transporting all these materials is causing a lot of emissions. And these emissions are the problem. And what problem do they cause? Okay, we have these greenhouse gas emissions, which is mainly CO2. There is also some methane and some N2O and some fluorocarbons, but the main topic is CO2. Now, what most people mess up is cause and effect. They say, I'm fighting against global warming. You cannot fight against global warming. You cannot fight against the effect. You must fight against the cause, and the cause is the emission. So the cause is here. And this is causing an effect, for example, an inhomogeneous atmospheric warming. And this is causing, in a next step, droughts. And droughts are causing, in a next step, decreased crop yield. Less wine, less apples, less wheat. And if you have a decreased crop yield, what does this mean? If your harvest is low, then people have hunger. And if people have hunger, the society either gets destabilized or the people get violent. And then your society falls apart. So there is a reason, which is the cause, the Ursache, which is the emission. And then this is spreading out like a virus on multi different levels, causing effects and effects, secondary, third, fourth level, fifth level effects. Yeah? The same inhomogeneous oceanic warming because of CO2. This is reduced fish harvest. What does this mean? Okay, some people get out of work, the fishers. If they get out of work, they either get violent or they start migrating. If they migrate, they arrive somewhere else and said, I'm a European, I want to live here. I have the right to live here. And then you have to build a house for him. And a school for the kids, etc., etc. Means then the material thing comes again. So and this is what you have to understand. You cannot fight against this and not look at this. You have to look at this, and then these problems grow smaller. If you solve this, then these problems are mini. But nobody is solving this, because the greenhouse gas emissions are, despite the Paris Treaty, not sinking, they are rising. So the problem is getting bigger instead of smaller. What should we do? Continue? Yeah. Look at this. What you learn, or don't look at it. What you learn is, okay, what is global warming? It is 1.3 degrees, 1.4, blah, blah. So what does this mean, 1.3 degrees? You know, 1.5 is Paris Treaty. We should not exceed 1.5. But what does it mean, 1.3? Okay, scientifically spoken, every day on all the meteor stations all around the world, you measure several times the temperature. Then to make an average out of it. So this is the average temperature over the world today. 50,000 meteor stations, added up their temperature data, divided it by 50,000, this is the average. You do this every day. Then sum it up, 365 divided by 365, then this is the average day per year all over the world. So it's the average of the average of the globe in a day over the year. So the number means nothing. It is a certain indicator, but not more. This is good, important to know. But the 1.3 is what? Now the IPCC is defining the 1.3 as the annual worldwide average temperature in 2024 minus the worldwide average temperature of the years 1800 to 1900. So this is the base reference temperature, and then you look how much did it change to here. And then the result is 1.3. Now it is obvious if you change the base reference, another number occurs. So NASA, which is doing a lot of research in that field, does not take the so-called industrial period 1850, 1900, as the IPCC does, because they say, in this period of time we did not have enough sufficient precise data, we take another reference period. Yeah, if you take another reference period, global warming is 1.4. The German Meteor Association takes again another reference period, then the global warming is 1.2. So all of them are right because nobody indicates what is the reference period. So always ask if someone tells you we are at 1.4, to which reference period. If you take reference period, the average of the year 2012, then you are at 0.3. So what are we doing? And then this number which we find out, this is the average of the average of the average. But how it is distributed over the globe. And I did this calculation with the software we got from NASA it was in 2023. For 1 month, so this is the difference between the period of 1881 to 1900 and 2023, June. And its distribution in this month all over the world. And what you easily find out is that it's getting hot and hotter the more north you come, that the Mediterranean area is really with 6 degrees delta hurt dramatically, but also the northeast of Siberia and Canada. Nobody's talking about this. Here in the southern part of France, in Italy, in Spain, you really experience that. Because the crop yield is decreasing, the wine yield is decreasing. This is the result. And there are areas where you have more or less nothing going on, like here in the oceans, it's even getting cooler, etc., etc. But now we look at this band here, where most of the action happens. And we ask the question, where is the food produced on our planet? And it is exactly here, what I call the 20 to 40 degree zone. I introduced this 20 degree north from the equator to 40 degree north, this tiny strip, which is from the southern to the northern end, only 2,200 kilometers. You can drive that with your car in 1 week. Very, very small, is where we have the highest temperature anomalies, where we produce most of the food, which will be affected by those anomalies, and where the majority of the people on the planet is living, 4.5 billion. Means the entire problem is condensed in the 20-40 degree zone. This is what you have to understand. And it's clear that when it becomes uninhabitable here, the people will not migrate to Africa. Because the delta is small here, but the absolute value is high. What we see is the delta values compared to former times. In Africa, it was always super hot, so it doesn't make sense, or it's not an advantage if we now have only 41 compared to 40 degrees in June, because nobody can live there. But here it is remarkable. If you have an average temperature of, let's say, 34 instead of 28, this will yield remarkable crop yield. And then you produce less wheat, and then you don't have enough to eat. If you distribute the food in the way the people do it. Maybe another story in order to give you a way of thinking. When the Ukraine war started, the Russians have been accused to have a blockade on Odessa, and there are 30 million tons of wheat. And then the entire media in the world said, hundreds of millions of people will die in the eastern part of Africa, Somalia, Ethiopia, etc., because they don't get the wheat which is in Odessa, and the Russians don't let them out. So it was, at least in the German media, Putin is a mass murderer and whatever it was. And I was obviously the only one in the Republic who said how much wheat is on the table. Not in Odessa, on the world. What is the annual wheat harvest? What would you estimate if you take the entire harvest of wheat divided by 365 days, divided by 8 billion people, then this is your personal rate in a basic democratic type of distribution. How much would you get? Is 1 kilogram. You can't eat that much. You will grow fat like a whatever. You can't eat that much. Even my Italian colleagues told me this is, even for an Italian who is eating pasta every day, absolutely impossible, 1 kilogram. If you distribute it democratically, the amount of wheat in the harbor of Odessa was half a spoonful to this 1 kilogram. So forget about this. So where does the wheat go? Into the stomachs of pigs and cows. More than 60% of the wheat production are fed to animals. This is why we have a shortage and the prices shoot up. If we think clear and we say stop animals feeding with this very important wheat, then the problem is gone. There's enough to eat for everybody today. Enough. It's a question of how you distribute it, and this is a question of how the society functions. Now we learned about these degrees, etc., and we learned a little bit about the importance of emissions. Now in Germany, many people say, what can I do? It is the Chinese. Yeah? The Chinese, there are so many, they are emitting like hell. I say, yeah, okay, if you compare Liechtenstein to China, Liechtenstein is always the winner. You cannot compare Germany with China, you have to compare person with person. This gives you the real impact. So if we compare person with person, then the average is 5 tons CO2 per year all over the world. The US has 16. Germany 9, China 7, Africa less than 1. The planet may take, depending on whom you ask, 2 tons. It can absorb these emissions with all the forests and with the seas, but not 5. So if you would do a ranking and a podest, number 1 to be, let's say, the only population which really takes care of the planet is the people of Africa. The rest are polluters. They are the shining examples. So, I think I jump a little bit over this because I don't want to overload you with information. There is a series of buildings I designed in order, not because I prefer residential buildings, in order to find out with a limited financial risk what is doable. And I already showed you the glass house I'm living in since 25 years. The house here was one of the successors. It is, whereas the glass house produces 100% of the energy it needs, this one produces 170. It is the first house in the world which can communicate with its electric cars. So whenever we have photovoltaic energy, the question is, should we put it in the battery? Should we put it in the public grid? What should we do? Then there's communication with the car. When does the car come home? What is the battery level? Should we feed the car instead of putting the energy to the public grid? All these decisions are made in a communication, the house and its car. 170%. Then I said, okay, we designed this, recyclable and so on, 200%, no chimney, emission-free. The first house in the world which communicates with the neighbor building, which is a house designed by Le Corbusier, 90 years old at these times, an energy sink like hell, but we have an overproduction with the new house, and on a short way cable, the new house feeds the old one. This is the technique we have to apply. Yeah, if you do so, then you can overcome many, many design problems you are typically sticking in, like oversized thermal packaging and things like this. The question is, if we have zero emissions, problem solved. If we don't need electricity from the public grid at a time when the public grid is critical, problem solved. It is so easy. It is so unbelievable easy. But nobody explains that to you. So we further developed these techniques which we applied in industrial production We produce modules completely equipped and pre-tested. So we guarantee once the model comes around the corner on a truck, 60 minutes later you might move in. The water is flowing, electricity is there, the light is working, everything. And this is high-speed building, which looks great. We installed one level in one day on this 340 apartment. So one level having 10 apartments in one day, 5 stories in 1 week. So we built 50 apartments, turnkey to move in 1 week. No problem. Just a combination of minimize material, use recycled materials, make it recyclable, avoid emissions in the production time, have no chimney, 0 emission in the use phase. Energy, why should we save energy? If we have enough solar energy, it's fine. The same is true with my glass house. This is an energy waster. I need energy like hell in wintertime. Yeah, so what? I have 160 square meters of photovoltaic. I have some warmth tank. I have an electricity battery. I don't need the public grid. I can cut off the house for a week, even in wintertime, from the public grid. And there is no insulation, except the window panes, which is a triple glazing, which was very, let's say, expensive. But it gives you a new impression, this is me in the center, on how to work, because you are embedded in nature and in the surroundings. You have another contact to what is happening around you. Good. What should I say? I jump over this in order to finish then, and then I let you go. But what is of importance is the following one. The alignment of how we have to build in the future is not a problem of building technology anymore. In the last decade, myself, in the last 3 decades, we developed these techniques of using less material to build for more, to build with recycled materials, to build in a recyclable way, to minimize emission in the production and waste, to have 0 emission in the use phase, to use energy which we produce by ourselves or in the neighborhood. This is all doable. The fact that we are buying cars which are bigger and bigger and bigger, the design of which is more aggressive and more aggressive and more aggressive, the fact that we do not, let's say, renovate or refurbish our houses in the way we should, is not a building problem. The tools and the methods have been developed, they are there. No architectural and no engineering problem. It is a sociological problem. Or are you able to answer the question, why is someone who has an academic career behind him, 2 doctor titles, making a lot of money, buying an SUV with a diesel engine nowadays? These people are polluting the atmosphere. This is the problem, and they don't change behavior because the entire society did not change its behavior up to now. We are still on the focus that the level of our consume behavior is defining the level of our social rank. This is the point. We have been educated, everyone has the same chance, which is not true, but let's accept it, everyone has the same chance, etc., etc. You just have to have tough elbows. We call that competition. And then you make more money and more money and more money. You become successful and successful. But if nobody knows that you are successful, doesn't make you really happy. You can go to bed, open your savings book and say, oh God, I'm that successful. typical measurement on societal success is your consumer behavior. Means, what car is he driving? Where is he doing his vacations? Does he have labeled jackets? Is there some Hugo Boss? There are even people which have Armani here and whatever. This is not because they are fans of Armani. This is showing to the rest of the society, this is my consumer level. I'm really successful. My hairdresser told me that his girlfriend is selling Hermes paper bags. So if you go to Hermes, buy some perfume, then you get these nice bags. If you cannot afford the very expensive perfume, you don't have that. So somehow they have a source and they sell the bag for 20 euros. And then people buy a paper bag for 20 euros just to be capable to walk in the city with that bag, to indicate their consumer abilities, means to define their social ranking. And as long as we define social ranking by consumer abilities, the thing will go wrong, definitely. Social ranking must be defined by something else, by protecting nature, by taking care of other human beings, etc., etc. But this means a rapid evolution, or if you speak these two words very fast, a rapid evolution means a revolution in the next 25 years, definitely. Remember what I said. Thank you.
Thank you very much, Werner. Maybe you have some questions?
No, the joints are made of the steel structure by bolting, by screws. So this is the one thing. Then, for example, the flooring is just an inlay. So we have wooden elements, 3 by 4 meters, and we just lay them into the steel structure. There's no gluing, no nailing, no bolting. If you have a suction device, you can lift up the floor, which is a big advantage because I have in total 36 of these steel grids on 4 floors, and I can change the floor layout easily by taking it up and moving it to the next opening or grid. Then the glass, of course, the glass is a little bit the problem because the sealant of the glass, this is a glue which you have to cut out. There is no industrial procedure yet. Saint-Gobain is developing one, but this is a little bit this thin. And the rest is just laid. There is no cables in the wall. We have an aluminum channel which runs around the facade inside with operable flaps. You open them and then you see all the electricity wiring and the warm and cold and wastewater pipes. So this is the famous bathtub because I have a bathtub on wheels. It's very well known in China and in Japan. Got many copies. So the bathtub can be plugged in to these water supplies which are available everywhere. So if you want to take your bath now in whatever south end of the apartment, you just unplug it, roll it over, plug it again. Which means, this is not because I'm mad, this is to test the sense of flexibility to the end where it starts not to make any sense anymore. So, there is not more. The roof ceiling is clamped on the edges, and the dead weight of the photovoltaic is keeping it in place. I apologize for talking that long, but since everyone was looking quite interested, I thought it might be interesting. And since nobody fell asleep, so je vous remercie. Bonne soirée.